Well, since everyone's quiet, how about we start the show? It is a show, right? I'm on YouTube. It's a show. My son is obsessed with becoming a YouTuber, and right now he's very mad that he only can post videos on his dad's channel, and they're locked down because his dad doesn't have enough subscribers to get ads to make money. And we tried to explain to him, no, we're not doing this to make money, pal. We're just trying to help people. Well, I want to make money. Okay, well, he's going to have to work on his YouTube skills, though, I got to tell you. They're not quite there yet, but so you don't have to have YouTube skills if you don't want to make money. That's the key. But let's see here. It's Thursday because it's not garbage day. So happy Thursday, our second to last Thursday together. I have the syllabus up to remind us of what is outstanding still. So homework 5, I will be getting those back to you soon-ish. I'm not going to promise when. When I get them done is the answer. But I know that you are awaiting the opportunity to make a revision, and so I will make sure that you have time to do that. Nikki is not able to do office hours tomorrow or Monday, so I added those announcements up here and on Icon. Your next thing to do is Formative Assessment 6, which is in Icon, and Vladimir is going to lead that discussion on Tuesday. Then we have Homework 6, which is newly available as of this morning. It's based on Example 6A, which we're going to start today. It's a path model that involves mediation. You can complete it using Mplus, Lavon, or Stata. I believe we have verified all of those packages, and the TAs have already done the homework, so they're ready to help you if you need help. So I don't know if you do that. I make them do your homework first so that they remember how to do it, and I can make sure that the answer keys don't have any problems. And then after next week, we have finals week, which is not finals. I don't do tests, but I do office hours. So you are able to find me during finals week during the times I would normally be teaching or office houring. And then everything needs to be wrapped up by Friday. At that point, I will grade whatever's outstanding, submit grades, and we'll be done. So we're almost there. Nikki says, can confirm it works in Stata. Yes. It does not involve any generalized outcomes, which means that the estimation routines are much more stable across packages when that is the case. It's generalized stuff, especially with latent variables where things get a little bit wonky. But this one is just a general linear model version. So that's what we got. So any questions on any of that or things I'm forgetting? Okay, bye-bye webpage. Then we get to keep talking about path models and model fit and stuff like that. Shall we? We shall. So these slides I didn't go over, so I realized I should probably do that. We're talking about model fit evaluation, which is a thing that we need to be concerned about whenever we're in a multivariate model. Model fit is all about whether or not the relationships that you've specified in the model for your variables match the relationships that are in the data. So it's not about whether you have a significant predictor, for instance. That's not what model fit is about. I know it's confusing. Model fit and effect size are two entirely different concepts. Model fit means that you have adequately recreated the relationships in your data regardless of how strong they are. Effect size is about how strong they are. So there's 4 steps, I would say, in evaluating a path model and a structural equation model more generally once you add latent variables. We've been through these steps, but just to make sure that I've covered my bases, assessing global fit is the first one. So that is the series of measures with lots of acronyms. So things like the chi-square test, which is a -2 log likelihood difference between the best possible model, that's called the saturated model, and the worst possible model, which is the null model. So that actually, let's back up 2 more slides. We'll start with this. Slide 20 is where I want to start. So if your model is over-identified, then you can assess fit. Over-identified means you've overlooked something. So you are missing some direct relationships between pairs of variables. Then it's over-identified. That means you have degrees of freedom left over. You have not estimated everything you possibly could. So once you're in that situation, all of the measures of fit are relative to 2 different baselines, the best possible model or the worst possible model. So best model is called saturated, When you get to the longitudinal class this fall, if anyone's coming to that, it will be called unstructured, but it's the same concept. It's the idea that if we just estimate directly in the data the means, variances, and covariances for all the variables, we find out how tall the data are under that model, and that's our new standard for as best it gets. Then the question is, how much worse did we do by estimating a model that has fewer degrees of freedom? The alternative is called the null model, which in most cases is going to be a model in which all variables get their own mean, they get their own variance, but there's no covariance whatsoever. So then the alternative is, how much better did our model do than the worst possible model? So we looked at measures that correspond to each of these benchmarks. So SRMR is how far off on average your correlations are relative to the best model, the perfect model. So we want these values to be as small as possible. RMSEA is another one that's relative to the best saturated model, and we want the values to be as small as possible. There's also a test of close fit for this one as to whether it's less than or equal to 0.05. You'll get a p-value for that on your output, and you still want it to be non-significant in that case. The other two comparative fit indices, so the CFI and TLI, those ones are relative to the worst model. So then it's how much better did you do than worse. So we look at those first. And I want to point out that each of these standards that is listed here for what is considered good enough, these largely came from one simulation study published in 1999. I wish I could have been this guy, right? Because I'd be set for life. This study has been cited over 100,000 times. Anyone who writes a paper where they have a path model or a structural equation model and they say, I'm considering RMSEA of this to be good, they cite this paper. But one paper can't cover every possible situation that you would find yourself in with these models. So their study was relatively limited. It involved latent variables that were very reliably measured. There were only 3 of them, only 15 variables in total. It was based with complete data, no missing data, and generated to be perfectly multivariate normal. So subsequent research has focused on extending these limitations, like what if you have a lot of variables? What if you have a lot of factors? What if you have this problem? What if you have crappy indicators? What if you have low reliability? Turns out that what is considered good fluctuates as a function of those other characteristics. So I just want to point out that there is a more current literature that's continually evolving as to what is considered good, and folks are heading to the point, I'm going to call on you in a minute, T, to try to customize, like, what is good for me and my problem with my variables. Right, T?
Right.
Right, so what are you going to do in your dissertation, and why am I calling on you?
Dynamic fit indices.
Tell everybody what that is.
So that is a way of basically, let me think about this for like 2 seconds.
Yeah, I should have warned you. Put her on the hot seat. She's not even in this class. She's auditing. And I'm still making her answer questions.
So basically, it's a way of generating like fit indices that are specific to your particular data and its characteristics. So that gives us like a more reasonable way to evaluate whether or not model data fit is actually good.
Mm-hmm.
Yeah.
It's through simulation, basically. So, and there are Shiny apps and R packages and things that do this. So I can point you in those resources if you want. I have a bunch of readings and slides about this in the structural equation modeling class that meets above this because we cover it in greater detail there. So just know that these standards, you know, are conventional, but they're not like ironclad. Just know that for now. So global fit is all about whether we have recreated the relationships in our data. If we haven't, then we got to figure out why. Like, where did we go wrong? And so that is called local misfit or localized model strain. And so this is looking at the very specific match between each correlation in your data and each recreated correlation from your model and seeing how far off they are. And there are a couple different ways that these results will be presented. One is normalized residuals, which function like z-scores. So they are a ratio of how far off it is relative to the standard error of the estimate. And positive values means that you are under predicting, like the 2 variables are more related than your model says. Negative residuals means you are over-predicting and they want to be less related or they want to be negatively related. So we can figure out why the model doesn't fit by looking at this more specific information. Then we get into the suggestions that are offered by the software, completely atheoretically and data-driven suggestions as to how you can fix your model. So I call these the cheat codes. They are more generally known as modification indices. I was in Germany a couple summers ago for a consulting gig, and one of the students over there was looking for the word modification and didn't come up with it, and they came up with manipulation indices instead, and I'm like, that's actually better. I'm going to call it that from now on. These are manipulation indices, how you can manipulate your model into fitting. They are known in the statistical world as an example of a score test. So we've seen likelihood ratio tests in this class. We've seen walled tests. That's the T or the F that shows up on your output, or the T or the Z or the chi-square. This is a third category of significance test. And they tell you how much your chi-square, which is the judge of fit relative to the perfect model, how much it would improve by adding whatever parameter. So it would go down if your model is improving. It would go up if it is getting worse. Cough, cough, homework question. So each of these then tells you what we can add, and we want to be very careful in adding these things to make sure that they make sense, that you can defend them in your discussion section, and that you would expect them to show up again in a replication of the study. So after we go through that process, revise the model until it fits well enough, and then we can interpret the relationships. We're not done yet. So step 4 is effect size. And this is exactly the same set of concepts that you're already familiar with. So in normally distributed outcomes, conditionally normal outcomes, general linear model land, which is where we are right now, we have R-squared type things, right? How much variance in this outcome did your model account for? We have individual slope effect sizes, such as standardized slopes or partial eta metrics, semi-partial etas, that kind of thing. And if we were predicting a binary outcome, what kind of effect size might we report?
Odds ratio.
Odds ratio. What if it were an ordinal outcome? Say it again.
Odds ratio.
Odds ratio. What if it were a nominal outcome? I'm pointing at people now. I left my conductor stick at home.
Ordinal?
What if it were nominal? Uh-huh. Say it again.
Odds ratio.
Okay, pointing behind you. What if it's a count outcome? Say it again. Odds ratio. What if it's a binomial outcome? Odds ratio. You get the point here, except they change names. If it's a count outcome, it's an incident rate ratio. But it's still e to the slope. So it's the same idea. So those would be effect sizes in generalized extensions of these, if this box were a binary outcome, for instance, or an ordinal outcome. So I showed you this slide last week to make a point, but now we can make the point more broadly. I have gotten this question over email several times throughout the years. My path model fits really, really well, but nothing is significant. How can that be? So riddle me this. How can that be? How can we have very good fit and yet have no significant relationships?
Because the model fit doesn't mean effect size.
Because model fit doesn't mean effect size, right? What does model fit mean?
How well the model reproduce something like that.
Yes, something like that. Want to phone a friend? Phone a friend.
James.
Okay, you've been phoned. How well the model reproduces is where we left off. You want to phone a friend too? Who would you like to phone? Okay, you've been phoned.
Successfully reproduce the relationships.
There you go. Successfully reproduce the relationships among the variables. More specifically, the means, variances, and covariances among the variables if you're in multivariate normal land. Yes. Suggestions, recreating covariant structure, that's a synonym I will take, means variances and covariances. Maybe not enough sample size. That could be if you're talking about significance per se. So if you have a non-significant result, it could be because you don't have a large effect or because you don't have enough people to detect it. So I'll give you that one as well. But yeah, what it would mean is if you have no significant relationships in your model and it fits really well, that means the null model holds. The worst model, in which you have a mean and a variance but no relationships, that's what your data would look like. So good fit does not mean anything in terms of how well you're able to actually predict the variability in your outcomes. What you are predicting is how much covariability there is. How much there is what fit is about. What makes it go that way is effect size. Two different things. So let's look at the remainder of example 5. So where we left off is looking at a model. This was M+ output in code here. Do we want to go back over the M+ stuff since that was brand new? Or do you feel okay with that? No one has an opinion. It's a forced choice alternative question. Either we feel okay with it or we'd like to go back over it. Go back over it. Okay, all right then. So M+ is its own standalone program. It's very expensive. It is continually being developed to add the newest and coolest stuff. That's why it's very expensive. But that also means the people who made it decided not to invest in the front end in terms of how the data manipulation part happens or the back end in terms of how the results happen. So you have to input text data, .dat, tab delimited, or comma separated values format are the two that are easiest. You can also do fixed format, but that's a pain and I would not recommend it. And each script is a standalone model. So you can't just run a piece of it, like in every other program, you can just highlight that line and run it. It doesn't work that way. It runs the whole thing from top to bottom. So if you wanted to have multiple models, you'd have to comment out the ones you don't currently want to run, and comments are exclamation points in M+ with this green, the green font. So I color these things so it'll be like what it looks like when you word the program. Because this is just a text file though, you can open M+ files in any text editor. You don't have to have M+. So once you run your model and save your results, you don't have to go back into it to get to those results anymore. So you input text data, and this is what the script looks like. The things in blue are keywords, the things in green are comments, and the things in black you would have to change. M+ is not case or space sensitive. So my philosophy is I generally use title case for variable names. I tend to use uppercase for commands that are M+ things so that we can sort of visually separate those two. So title is the first thing here. This is optional. This is just like for your own record keeping. It will show up on your output. You can have it or not have it. Text can only go 90 characters across. So if you put anything about a model that's longer than that, it will quit reading and it may break the estimator because it doesn't know what you're intended to do. So if your M+ script, which is .inp extension, is in the same folder with your data, you can just say what the name of the data set is. If it's not, you need to put the entire path to that place. Under the variable section, we need to tell it what the names of the variables are in the order in which they appear in your file. So if you want to use M+ for homework 6, instead of having a starter syntax in all the other programs, I built one for M+ that gives you sort of this shell to work with that has the names of the variables in the story problem that is for homework 6. So we list them in order. Each name can only be 8 characters or fewer. Used variables then subsets this list to just what you want in the model. So if you forget this, it will put everything in your data set into your model, including the ID variable. That may cause problems. If you have any missing data, it does allow you to have blanks or dots, but I have found that that screws things up. So superstitiously, I always replace my missing data with some kind of indicator, usually -99, some number of 9s after that. Within homework 6, I included code for those of you who are using Stata or R to replace those 99s with dots again, so that it doesn't screw up things in those programs. Under analysis, you can tell it what kind of analysis you want for this purpose. A type, what is the default, type equals general is fine. Estimators, maximum likelihood is what we're using. There's other choices that we'll get into a little bit, maybe not a whole lot. Output is asking for extra pieces of things. Unfortunately, within M+, you can't shut off the default output. There's a whole bunch of extra stuff that it prints. So don't ever try to print an M+ output file. You will waste all the paper you own if you try that. It's voluminous. It's huge. But I'm asking for confidence interval, standardized solution, residual. This is the keyword that gets you local misfit information. So how far off each predicted correlation is, or each predicted covariance. And then mod indices are the cheat codes. 3.84 is the chi-square critical value for the improvement at 1 degree of freedom to be significant at the alpha equals 0.05 level. That's where that number came from. So it says, only give me a suggestion if it's going to help significantly, is what that means. In the model itself, there are very few conventions that you have to learn. So there's a lot of like implicitness here. I try to write out everything so that it's explicit, but it's way more text than you would have to write in most cases. So when you refer to the name of a variable, such as these 3 marital outcomes here, by itself, what you are referring to is its variance, if it's a predictor, or its residual variance, if it's an outcome. So I'm asking for leftover variances to be estimated for all 3 of my outcomes, the same as usual. With, remember what that one means? As a keyword, there's only 3 keywords you have to learn, with, on, or by. What does with mean? Covariance, yep, 2-headed arrow. So a stack of variables with with in the middle and then the same stack of variables means give me all possible covariances among them. As an aside, another option that you will see, not in this example, but sometimes, is the word p in front of it. P with, that means pairwise with. So then that would do kid marital with this one, the second one with the second one, the third one with the third one. So that's helpful if you have like a longitudinal study where you want like the first occasion of this one to be correlated with the first occasion of that one, something like that. Intercepts or means is what you get when you list the name of the variable in a bracket. So these are brackety things here. Because these are outcomes, what I'm asking for is their intercepts specifically. And then the keyword on is a regression. And it's always in the order y on x. So think of on as an equal sign in an equation. Then you'll get the order right. So you can stack up your outcomes on the left-hand side of on, or you can stack up your predictors on the right-hand side of on, or both. So I have 2 predictors of 1 outcome in the first line, 1 predictor of 1 outcome in the second, and then 1 predictor of 3 outcomes in the third. So it's just multiple regressions happening simultaneously. And in this model, every variable is either a predictor or an outcome, but not both. In the next example I have, we'll have examples of where predictors function as outcomes as well. Last but not least, model constraint, which is an M+ command, but it doesn't turn blue. I know, model turns blue, but model constraint doesn't. This is the analog to estimate statements in SAS, GLHT in R, LinComs in Stata, test in SPSS, and every package has an analog to this if you know how to find it. These are linear combinations. M+ allows you to do nonlinear combinations as well as to do combinations of variance components, so it's more flexible than what the other programs offer. This is an example of how you would get differences between slopes. I will show you how to use this same technique to get estimates of indirect effects in mediation models in the next example. So this is a multivariate regression with 4 different predictors and 3 different outcomes. That's what this is. So in terms of model fit, zoom in here. We have log likelihood. In this metric, is bigger better or is smaller better? For a homework question. Log likelihood is the height of your data given the model parameters, where height in this example is defined by the multivariate normal distribution.
Bigger is better.
Bigger is better. Is it good to be tall? I wouldn't know. I'm asking. I think it should be, right? I actually wish I were either an inch taller or an inch shorter, because I'm right on the line of between petite pants and regular pants. So petite pants are too short and regular pants are too long. I just want to get off the fence, like one way or the other. But the good news is I'm aging rapidly, and so I will continue to shrink as I get older and older, so eventually I will be a true petite. But yeah, taller is better. And here is, I want to tell you a story to help you remember for the rest of your life which one is yours for your model. So I had the hardest time remembering this, even though I teach this stuff. Like, am I the HO or am I the H1? Because you get two of these. One of these is for you, and one of these is for the best possible saturated model. So one day at the University of Nebraska, I was holding office hours, and I used to hold them in a computer lab like this so I could help as many people as possible. And I was helping someone across 2 different classes, and one of the students, Lindsay, hi Lindsay, if you're listening, she knows I tell this story. She looked up at me and she said, am I the hoe? I'm like, what? What are you talking about? NM plus, am I the hoe? Is your model the HO model? Is that what you're asking me? Then yes, you are the hoe. Okay, thank you. So I will never forget it now. I'm the hoe. Just write that down. I am the hoe. And I forgot to bring it, but I actually have a gag about this. So I went to Kohl's to pick up an online order, and they put your last name, the first 2 letters of your last name, on the outside of the bag so that you see it. And you know what it said? I'm the hoe, because I'm Lisa Hoffman. So I saw that, and I'm like, oh my God, I gotta bring this to class. Yeah, so I am the hoe. This is my model. The alternative is the H1, which is the saturated model height. So this is as tall as your data can get. Okay, this is the right answer. The question is, how close did we get to right? How much worse are we? How much shorter is our log likelihood than the best possible one? And we don't have to figure that out ourselves. M+ and the other packages as well figure that out for you. That is what this chi-square test of model fit is telling you. This is the difference times -2 in the log likelihoods given right here. So this is distributed as a chi-square. We have a, let's call it a non-significant result, but just barely. P-value of 0.09. Is this good news or bad news that it's non-significant?
Good news.
Good news, yes. Because it means we are not worse than perfect. It's backwards from how you're used to thinking about it. So this is marginal though. I'm not going to accept this at face value. I'm still going to look at the local fit and make sure there's no big problems. Degrees of freedom. That tells me how many more things I could still add. That's how over-identified I am. I could add 6 more parameters to my model, 6 more relationships between variables that are not there. RMSEA, we want this to be small. This would be conventionally okay, less than 0.08-ish, 0.05 is the goal. Here's another example of a p-value we want to be non-significant. This is called the test of close fit. So we are not worse than 0.05, that's good news. The alternative fit indices, how much better are we than the worst model? That's CFI and TLI. We want these to be as close to 1 as possible. So these aren't very happy with us. This one you can completely ignore, always. Just cross it out, just disregard. This is asking about the difference between the saturated best model and the worst null model. Not you, has nothing to do with you. If this is non-significant, then you should take your ball and go home. If the saturated model is not different than the null model, that means you have no covariance worth modeling. The null model says there's no relationships in your data. If that fits as well as letting the relationships be there, you have no relationships. You have nothing to do. I've never seen that happen, but I guess that's why they give it to you. I don't know, as a check.
So for this,
Mhm.
significant is good.
Significant is good. That means you can keep your ball in play. Yes. SR-MR is how far off on average your correlations are. So we want this to be small as well, and this one is reasonably happy. Less than 0.6 or so is a conventional thing. So the first part of the output then, let me get this back, let me zero out here. Estimate, that's the estimate of whatever we've estimated. That label is not going to help you though. So this is where the rows have information about what the estimate is of. Standard error is the next column as usual. The estimate divided by the standard error, what would I normally call that?
Z-score.
Hmm?
Z-score.
It would be either a T or a Z. A walled test would be the term that I would use. What would dictate if it's a T versus a Z? Treat it as a T versus a Z, I should say. It's the same number regardless. Mostly this semester we've had Z's. If you're doing a regression though, you would have a T. What's the difference? You would have one more column here sometimes if it were going to be a T instead. Yeah, like a T test statistic. That is an impossible phrase for me to say. This one, well, this is two-tailed. You could have a one-tailed test, but that's not where I'm going with this.
Z-score focus on the height.
Higher what?
The height.
Height. I'm not, keep talking. Not sure what you mean yet.
I think the difference between the t-test and the z-test is the z-test is more focused on the height.
Oh, the shape,
Yeah,
you
shape,
mean?
yeah.
Yeah, so Z is always Z no matter what, right? Like there's only one Z, but T is like increasingly flat as a function of something. What's the something?
What I recall is we use T when the sample size is small.
Yes, we use T when the sample size is small because T has a different distribution based on, we're almost there. Sample size, yep, but I'm looking for one more term. What would you call sample size minus the number of fixed effects in your model? There we go, we got it. Yes, degrees of freedom. Not the same degrees of freedom in a path model, mind you, which is the number of variables and the number of parameters you could still add. This degrees of freedom would be about the number of people. So yes, Z is when you assume you have infinite people. T is when you pay attention to how much people you have. After you get past, I don't know, like 100 or so, they start to converge onto the same thing. So there's no denominator degrees of freedom being used here, as there hasn't been in most of the generalized models as well. So this is being treated as a Z in this case. And then the next column is two-tailed p-value. And this column does not exist. This is me being nice. So the interpretation notation column does not exist, but this is me trying to tie it back to the equation for you.
If we use T, what's the line we'll added after the estimate standard errors?
You would have a column for denominator degrees of freedom.
Okay.
If it, so like in mixed models, it's going to be parameter specific what that would be. In a regression model, it's usually given separately because it would be the same for all parameters, but it would be given somewhere what your degrees of freedom are with which to compare your T to that right distribution. So what is this an estimate of? That's the question. And it's like, Kid Marathon Kid Boy. So in English, what are these three numbers? Slopes.
Inter-
Yeah, say it again.
Intercept.
Nope. These are not intercepts. These are slopes. Ons are slopes. So it is the y on the x's, is how you would read this. So this is the regression model in which the kid outcome is being predicted from the kid's gender, the kid's education, and the dad's education. Likewise, this is the regression model in which the mom outcome is being predicted by her education and dad's education, and then dad's education is predicting his outcome. With, what must these be? What are these numbers in English? I guess it's English. It's kind of not. ¿Cómo se dice covariance in español?
Covarianza.
Covarianza?
Almost the same, yeah.
Okay. Oh, so it could be English or Spanish.
Yeah.
Any other languages? What's covariance in another language? Those are the only two I got. Any ideas?
斜方差 in Chinese.
Say it again.
斜方差.
Yeah, I'm not going to try. I'm sorry. Okay, covariance in Chinese as well. Yeah, these are covariances. Pick your language, but what I will tell you is that if you make a table for a paper and you just write this, your readers will be like, what is that? That's what they'll say. So the heading would be covariances and then the list of parameters. So these are residual covariances. This is how much the three outcomes are still related after controlling for all the things that predict them. So yeah, it looks like kids and moms are not related, but kids and dads are and moms and dads are. So after controlling for this stuff. And the Zoomers have typed the pronunciation for me. Yeah, thank you, but I'm still not going to do it. I'm going to murder it. It's not going to happen. All right, here's where we get to intercepts. They get their own proper label. Thank you, M+, for doing us a favor. So these are the same intercepts we've been talking about all semester. These are the expected outcomes when the predictors are 0. So on a scale of 1 to 4, this is the expected amount of conservative attitudes for the adult children, for the moms, and for the dads, conditional on their education variables being centered at 12, and for adult children who are women, I believe. And then residual variances, those are also labeled accurately. So this is the amount of variability in each outcome left over. The last section here is the additional requests that I made under model constraint to get differences between slopes. So the only one that's significant is the effect of education for the dads is stronger than it is for the kids. Then we get to the standardized solution. It's the exact same set of results in the same order on a different scale. So in regression, if you're used to looking at standardized slopes, this is what these are. So in path models, people often make note of these because then the variables are theoretically on the same scale and you can compare across them. So these would be considered indices of fit or indices of effect size. These are indices of fit or indices of effect size, standardized slopes. Don't think too hard. I meant this as a softball. Vladimir, I'm going to call on you.
Effect sizes.
These are effect sizes. Why aren't they indices of fit?
Because we don't have that assumption in our model.
Well, we,
That they fit or not.
yeah, well, we are over-identified. We can test fit. But yes, these are associations among these variables in a scale in which all variables have a mean of 0 and a variance of 1. So they're all on the same scale. Yes.
I have a quick question, Lisa.
Yeah.
So here we know that those standardized slopes are going to reflect the relationship between the predictor and the outcome.
The unique relationship between each predictor and its outcome, yes.
That's my question related to. That unique relationship, what's the meaning of that? Is something like a partial correlation, semi-partial correlation?
It is neither of the above. But it is so unique is my shorthand for saying after controlling for other predictors, this is what this predictor's relationship is uniquely to that outcome.
Great.
Like if you picture a Venn diagram with overlapping circles, like this is the area that the other predictors didn't get. The problem with standardized slopes, though, is that the entire variable's variance is standardized to 1, not the unique part that this slope represents.
You mentioned that. I think.
Yeah, so it's really not what people think it is. And if you were to say, well, why don't we just standardize the unique part of the variance and do that? That's what a semi-partial correlation is. So I actually prefer those as measures of effect size because they're commensurate with how we're thinking about these effects.
Thank you.
But you don't get those out of software, so, yeah. For better or worse, everyone reports standardized effects because then they can say, look, this effect is bigger than that one because they're on the same scale. What do you call a covariance that's been standardized? See, you thought you were going to learn path modeling? We're back in intro stat again.
Correlation.
Yeah, these are correlations. Residual correlations, in fact. Intercepts and residual variances we don't usually do much with in the standardized solution, but we do R-square. Yeah, I was like, oh, I know that one. That looks familiar. Thank God I get something I recognize out of this. And I got 3 of them because I'm fitting 3 regression models at the same time. So this is the proportion of variance explained in each of these things. And this is actually something you don't normally see, a significance value directly for the R-square. Normally we get that for the F-test for the model, but this does it as part of the rest of the routines. So it looks like we have not explained significant variance in anything. Wah, wah. Now, why is our model not fitting as well as it could? That's our next task. So this is the residual output, in which the word residual in this context means discrepancy. It is how wrong we are in terms of how our model has recreated the data. So for the means of these outcomes, we are not wrong at all. And actually, it should just be the first 3. It prints it for the predictors too for no apparent reason. So for the means of these outcomes, we're not wrong because each outcome got its own intercept. So therefore, the means are going to be perfectly recreated in most cases. Likewise, we're not going to be very wrong on the variances. So these are on the diagonal here, trying to highlight the diagonal, because each of these outcomes got a separate residual variance that can just plug the hole as to however much is left over, as opposed to trying to constrain it to be equal or something like that. And I've highlighted the ones that are relatively biggest as to why our model does not fit as well as it could. It is the relationship between mom's education and specifically dad's marital status, but also to some extent kids and hers. So mom's education is already predicting the mom outcome, but the relationship is wrong. Okay, so there's 2 reasons why you can have this kind of local misfit. One is you forgot a relationship between those 2 things, which is the case. We don't currently have, we don't currently have mom's education predicting dad's marital status at all. Like that path is not there, and this is how wrong that is. We need it to be there. There should be a negative relationship there. And these are in, this is a covariance metric that I have this in. But this one should concern you. That's in the model. We have a direct relationship of mom's education predicting mom's outcome, but it's not the right one. So this is why we don't interpret the results until the model fits, because the results are not going to be right. They're going to be biased by whatever's missing. And the cheat codes are like, hey, you know what you should do? You should let mom's education predict dad's marital status. Or you could let mom's education correlate with dad's marital status or marital outcome. So basically, a one-headed arrow or a two-headed arrow would fix it, is what they're trying to say. It would not fix it to the same extent, though. A two-headed arrow, it looks like it would fix it slightly better, given everything else that's in the model. But either way, that's the relationship that's missing.
I have a question.
Hit me.
So on statement and with statement, right? When we fix it, do we fix like say, do we fix both? Like that is on mom and that is married on mom education, or do we just pick the with one? So it's like which one should we pick, or should we pick both?
You cannot pick both because they're redundant. You can't
Okay.
have a covariance and a slope between the same two variables because then they fight against each other to capture their direct relationship.
So which one should we pick?
In this case, I would pick the on. I would pick the slope because that's consistent with how we had education as a predictor of the outcomes for everybody else.
Got
To change
it.
that pattern would be weird and inconsistent,
Got it. Okay.
in my opinion. That's my example. I can do what I want. So let's fix it. So I'm going to show you how to fit the exact same model in Stata and regression software and in R, what are we in, Elmer? Trying to remember. What class is this? Oh, GLS, that's where we are, okay. As in path analysis. Did you have a question?
Yes,
Okay.
so let's say we do the model and we found that, okay, we're not predicting the best. Would you still report that in your, like, if you were publishing this? Like, it said that this would be better, so I'm gonna do this instead, or do you just forget about that and then go with this new model?
So the question is, how honest are we
Yes.
in describing the revision process? I will give you the preferred answer is yes. Like the way it should be is you start with a model that addresses your research hypotheses, you fit the model, you report that it didn't fit, you report the process of looking to see why it didn't fit and describing how you changed the model, and then you describe what happened. Yes. In practice, people are not always that forthcoming. If you want to have a middle ground, because being honest takes too many words, maybe preliminary analyses suggested that the model needed this, and so we added it, and here's what we found. Maybe that's a intermediate ground. In practice, anything that you think the reader should know but you don't have room for can now be put on online supplementary materials. So I've used that to sort of explain more about something that I didn't really want to focus on, but I felt was part of the story. Yep. Good questions. So even though it was only this latter parameter that was causing the misfit for symmetry, I went ahead and added mom's education to the kid predictor too, or the kid outcome too, because why not? So those are the two new slopes. So we're fitting the model in mixed. So we have the 3 people as fixed intercepts here. So each person is getting a separate intercept because we killed the global intercept. Then we have the dummy code, what looks like interaction terms. This is how we make each slope specific to each outcome. These are not interaction terms. These are main effects. The C.kid, the C.mom, and the C.dad act like switches to turn it on for that outcome. Because remember, in this version, it's long data, where every row is a separate person's outcome. So the 2 new ones that we added were at the bottom here. And then I did a whole bunch of extra stuff, predicted outcomes so that I could examine in R-square. In R, I'm using GLS because that was the only way I could find to allow residual correlation as well as separate variances per person. Killing the general intercept is accomplished by this 0 right here. And then we have the 3 intercepts and then what looks like the interaction terms, which are person outcome specific slopes. Bunch of stuff with that, asking for correlations to generate R-squares and things like that. In Stata, here is the path model version of that. So this is, I think, path analysis to me is much more understandable than stacking your data and tricking it with dummy codes. I wanted to show you both though because one or the other may be more convenient in a particular situation. But the reason that you could do it either way, as a multivariate regression and stacked data or as a path model, is because in this analysis, each variable is either a predictor or an outcome and not both. If a variable has to do both, that has to be a path model. That's the next example. So let's see, in Stata, I'm making the predictions go in the same order as the other packages. So it's Y and then an arrow pointing to Y and then X are the predictors on this side. The var statement asks for residual variances. Covariance asks for residual covariances. And then here are lincoms that show differences in slopes as an example. In the M+ code, everything is the same in terms of data variable and output, although I switched the estimator to something called robust maximum likelihood. So this is an option that corrects your fit statistics and your standard errors for deviations of multivariate normality. I use it as a default most of the time when I path model because if your data actually are normal, then it reduces to straight ML. So you're not hurting anything. So the new relationships that we have are in this last line of regressions here, these on statements. Everything else is exactly the same. Here are the differences among the slopes that I wanted to get. Then we have Lavon code. Who wants to learn Lavon? I'm like, no. One person. I hope you like green. Yeah. Either that or you need to go into RStudio and like, you know, mess with it so that the colors change how you like them. I know that's a choice. So do you remember the most important thing about Lavon code?
The squiggles.
Find where the squiggle key is on your keyboard. I believe it's called a tilde. So squiggle squiggle is how you tell it variance or covariance. It's variance if the two variables on the opposite sides are the same, because like a covariance of a variable with itself is its variance. Again, back with introstat. So these are residual variances. These are residual covariances. And we discussed last time you can stack them up on the right-hand side with plus signs, but not on the left-hand side. So this is not literal addition. This is, I want it with this one and I want it with that one too. It's a list. I know it's clumsy. Wait till you get to SEM and then they put plus signs in as factor loadings. That really gets people confused. Squiggle 1 is how you talk about intercepts. Two variables with one squiggle is how you tell it you want a slope. So this is the kid outcome being predicted by the two kid predictors. Then we have each of the other people's outcomes being predicted by education, and then the mom, new effects are right there. Non-squiggle, colon equals sign, which sort of looks like a face to me. Like, you know how you did emoticons in the 1980s, and I still do? It looks like they're, like if you turn it sideways, it looks like Kevin in Home Alone or something. So, you're making me linear combinations? Ah! So these are new things that you're asking for out of existing model parameters. You're asking for them to be combined in whatever way. And this is an example of how you would get a difference in slope for a contrast of effect size across these outcomes. Question, do we need to put all the green part in when we run an R? No. I don't like memorizing defaults because they change over time. So I write everything out, but no. In reality, I think what you would have to write are the regressions because it wouldn't know what you want for that for default. Intercepts are a default, you don't have to write that. Residual variances are a default. I'm not sure about the covariances. Vladimir, do you know? No? Okay, he doesn't know either. So you can go into the Lavon code and figure that out though. And by the way, if you haven't noticed, let me open up the class webpage again one more time. I have a list of all the packages that we've used in this class in this box. And this is all the documentation to each of the things. So yeah, I was just talking to Jonathan this morning about like the different classes and whatnot. This is the hardest class that I teach, generalized. I teach 6 different classes, and to me, this is the most challenging, and this is why. When you see it, like, these are all the different packages we've used this semester. It's like, oh, yeah, that does get a little tricky. The first time I taught it, I also used SAS for everything. So I was doing everything 3 times, which was insane. Now I'm just down to 2, but we're at 3 now because we picked up Levon, or M+. But yeah, Levon is right here. So you should be able to look and figure out what the defaults are in that. Yeah. Levon has a bunch of more specific functions that also have more specific defaults. Like there's one for growth models, there's one for structural equation models. I'm not sure if there's a path model one, but Levon as a function is the most generic and has the most flexibility. So once you write your model, then you feed it into the Levon call. So you tell it your data and then model equals. So you don't write like a formula like normal, you write the syntax object that you saved your model to, and it processes it from there. This is a typo. This should be MLR as an estimator in this one. So please add an R there, and I will repost this after class. Because I wanted to make that a point. Summary, I'm asking for measures of fit, R-square, etc. Modification indices, as well as residuals to look at how wrong we are still, even after we put in these 2 new slopes. So in Levon, this is Levon output. I don't think I've shown an example of this yet. It has 2 columns when you invoke robust maximum likelihood. The left column is like straight maximum likelihood, assuming that everything is perfectly multivariate normal. That's in the likelihood. The robust column over here is adjusting if it's not. So you can literally compare like how your conclusions would change as a function of using the robust. And if they changed, you probably need it. So either way, let me zoom in a little bit to get the numbers. We have, and I'm not kidding, this is what they called it, model test user model. Yeah, that face, like what? This is your chi-square of how much worse you are than perfect. This is your likelihood ratio test against the saturated model. Standard ML says we have a chi-square of 1 with 4 degrees of freedom. So previously it was 6 degrees of freedom, but we added 2 more paths, and so it went down. This is how many more we are missing, what we could have added. But we have a p-value that is 0.9. Good news or bad news? Good news. We are not worse than perfect. That's what that means. We win.
So does that mean if the number is bigger, it's not better, or just non-significant is the information we need?
I think the number matters. Like this is really non-significant, but I bet people would be like, you can't talk about it that way. Traditionally, in the framework of null hypothesis testing, it's a binary, it's significant or not based on your alpha, right? But like if you think of this as kind of an effect size for how wrong you are, a p-value of 0.06 to me is different than a p-value of 0.9. Like we're really not wrong. The lowest that chi-square can be is 0. That's perfect. Like not wrong at all. So, and if I do the robust version, still not wrong. Hooray. Now there is this extra thing here called a scaling factor, and if you do likelihood ratio test using robust ML, you have to incorporate it. I'm not going to talk about that in this class very much, but that shows up in the SEM class more. I think I threw it in the slides though for this class because I knew it was coming. So then we get model test baseline model. This is the one you can ignore. User model versus baseline model, that means comparative fit. So these are 1. That's as good as it can get. TLI is actually above 1. That happens. It's non-normed. Here's some robustified versions. I don't know what these are. They're different somehow. I haven't seen those in other packages. Log likelihood. Remember, which one are we? Which height is ours? We are the hoe. That is correct. So you're never going to forget. Even if your last name isn't H-O to start with. We are the hoe. RMSEA comes in a couple different flavors. We want it to be as close to 0 as possible, and lo and behold, it is. And then someone made up another kind. I don't know what robust means, because it's robust in the robust column, and then there's a robust to this. I'm not sure what it's robust to, but it's happy to, whatever it is. And SRMR is also happy. Here's the Lavaan output, where it does not label things super great, but it does label, this part says regressions. Oh, that's a word I know. That means slopes. I know what these estimates are. And look, it calls it a z-value. That's nice. And then that's called a p-value. That's maybe less nice. Also asks for confidence intervals, and then the very last column is where the standardized estimate is. So they put it all in one table instead of 2 separate sets of output, which is very convenient. So in terms of the new relationships, we have mom's education predicting dad's and predicting kids. Those are the 2 new ones. And it looks like the one predicting the kid is not significant, but the one predicting the dad is. So that is the difference in why our model fits, is because now we've adequately represented that relationship, which should make all the others more accurate as well. Residual, so covariances is right here. By the way, do you see how some of them have actually in this example, they all have a dot in front of them? That means they're residual covariances. If they don't have a dot, they're just straight covariances, not the leftover covariances. Likewise, intercepts with the dot mean they're actually intercepts. Or, yeah, these are covariances. Yeah, these are variances. And then R-squares. So we get all the same stuff. And then we get the defined parameters. These are the slope differences that I asked for to compare those. This piece of output here is the residual matrix. So this is literally how wrong we are in every spot. So all that's left is to have kids' education predict mom and dad outcomes, which we do not have. And we could potentially have the gender of the adult child predict mom and dad outcomes, and we already tested that earlier and found they're not significant. So it looks like most of these are reasonably ignorable since our model fit is nearly perfect. So we're still, these 4 things are still off because they're not in the model. But the fact that the model fits means they don't need to be. And here is a very brief results section, since most of these things are not significant. But here's my picture. So in practice, you can put the actual slopes on the lines in the picture. You can do it yourself manually if you have the patience, or you can try to get the software to make a diagram for you that has the path estimates on it. Most of them will do some version of that. As I had mentioned before, this right side here with the line and the arrows coming out, this is my cheaty way of saying I want all 3 of these things to be correlated rather than drawing 3 curved arrows. So this makes your diagram a little bit neater if you have a whole bunch of covariances among the same things. Note that there are no covariances shown on the left-hand side. All of these variables are predictors only. They are not in the likelihood. That means their means and variances and covariances are not things we are trying to find or worry about. And that's it. What do you think? Think you can do this?
I have a question. So when you see we see the figure 1, right? So those lines, how do we draw that? That we draw that based on our assumption or based on the results?
This is the model. This is a diagram that corresponds to the model that is the last model fitted, model 4, whatever it is. I think it's 4. That sound right? Sure. So yes, I made the different arrow patterns so that I could visually separate the lines a little bit, otherwise it starts to get cluttered. Another thing that I will do is any path that turns out to be non-significant, I might turn into a dotted line, and the significant ones I make like a stronger line, sort of visually separate them. I don't like the practice of no path if it's non-significant because you're not sure if it's in the model or not. That gets confusing. So this is a depiction of what our model is doing, like graphically. And I think that like showing this to your reader will help them orient like what the role of the variables are. So I recommend these sorts of paths as a starting point. And to be honest, when you do your final homework, make a picture first. I have a long list of slopes and stuff that I want you to put in the model. Make a picture first and then write the code from the picture. That's my recommendation. That is exactly how I did my own homework. Draw the picture and then write the code from the picture. All right, cool.
So like in the picture?
In the
Sorry.
picture.
Would you include both standardized and unstandardized estimates?
No, I'd pick one or the other. You should report both somehow. So if you're going to have a table of unstandardized estimate, standard error, you could put the standardized estimate next to it. Then you could put one or the other in the picture. Usually it's standardized is what people put in the picture. Up to you though.
That's good, thanks.
Yeah, so in terms of what you would need to report in results, let me just mention that. There's a whole bunch of columns here, right? More than you would typically see. You only need a couple of them. You need estimate, and you need standard error, and you need the standardized. That's it, those three. Do you know why? The others are all derived from them. Estimate divided by standard error is your z-value. If you know your z-value, you can look up what the p-value would be that corresponds to that. Confidence interval is estimate plus or minus 1.96. In this case, I think it's a 95% confidence interval, the standard error. So this can be computed from this information. There's two different versions of standardized. In this example, we want standardized equals all. That one would be harder to get because you would have to know the scale of your variables, and so throwing your reader a bone by giving them that one would be nice. So 3 columns, estimate, standard error, and then standardized. And then if you have room, maybe the exact p-value. If you don't have room, a star or a letter or something. I don't like the thing where it's 1 star for less than 0.1, or 2 stars for less than 0.05, or 3 stars for less than 0.01. Like I feel like that gets confusing. So I just pick something and go with it. I like to report the exact p-value when I have room. I also have gotten in the habit of bolding things that are significant, and nobody's yelled at me yet. So as a reader, I appreciate that. Like, pay attention to this one. You know, that helps visually. All right. Where were we in this? If there's anything else I need to say. Not really. We will talk about this later. Complications and generalized outcomes can wait until we have path models with generalized outcomes, I think. We don't need to get complicated at 3:10 in the afternoon on a Thursday, do we? No. No. Yeah, it does get worse if you're thinking, what? We haven't gotten to complicated yet? No, we have. All right. Any questions for our last 4 minutes of the week here? No. Well, if you think of any, please let us know. Please work on Formative Assessment 6 for Monday so that Vladimir can talk to you about it on Tuesday. Please start working on Homework 6 if you'd like to procrastinate on something else in your life. We'll be happy to help you with that as well. And I'll let you know when your Homework 5 feedback is available. Okay, then thanks for being here. Have good weekends. Bye for now. You too, have a great weekend.